Hi, I'm Alec Brown. I'm in the Electronics Engineering Technology program, and this is my presentation on my cooling tower water treatment using programmable logic. So here's a general outline of this presentation. So we're going to start with the introduction and research, move on to the system design, and then I'll show the operation of the system. In water cooling towers used in industrial applications, continual use can lead to scaling, fouling, and corrosion inside the towers. These undesirable effects can lead to expensive equipment repair and plant downtime. This presentation will discuss the process of combating these problems with an automated system run by a programmable logic controller that can prevent the listed problems by measuring conductivity, measured in microsiemens per centimeter, and monitoring the number of cooling towers active. Furthermore, this presentation will analyze the effectiveness of the PLC bleed and feed system used to lower the conductivity and pH levels of the cooling tower water by graphing the conductivity level over time with an emphasis on the regions where the cooling tower treatment is active. The results of this presentation should display the effectiveness of this project and map out the process used to achieve these results. So first, let's look at how cooling towers work in general, and what is conductivity, and why a water treatment is needed. So a typical cooling tower operates by adding warm water into the top of the cooling tower and letting it fall onto slats on the side. When water droplets fall on these slats, it increases their surface area and makes it easier for the water to cool. The water is then actually cooled when the water droplets encounter ambient air that flows into the tower, and this causes a small portion of the water to evaporate, and this causes the cooling action that lowers the temperature of the remaining water. And at this point, a fan blows out the evaporated water, and the cooled water collects at the base of the cooling tower. And this basic operation can kind of be seen from the diagram on the left. And then on the right is a picture of the two cooling towers that this water treatment will be used on. So since the cooling tower has to be exposed to the open air to cool the water, it can be exposed to any number of contaminants from the environment, such as dirt or microorganisms, along with whatever contaminants got into the water through the plant's processes. So if this is left unchecked over time, it can create problems such as fouling or scaling. And that picture on the right is a picture of untreated water with a lot of contaminants in it. So one of the best ways to check for contaminants is measuring conductivity. Conductivity is defined as the measure of the ability of water to pass an electrical current. And this value is higher when there's stuff dissolved in the water, because contaminants that are dissolved in water create ions, and those ions pass electrical current better. So this gives you a good gauge of how many pollutants you have in your water. And then once you know if you need some water treatment, the type of water treatment we used in my project is called a bleed and seed system. So this is basically where you're bleeding water, so you're getting rid of some of that contaminated water, and then you're seeding the cooling tower with chemicals that will help to lower the conductivity. Now let's move to the system design. So this is going to consist of showing some wiring diagrams, pictures and schematics, and just talking about how the projects work in general with the equipment. So here's a complete parts list and cost analysis for all the equipment used in this project. And be basically categorized into the conductivity sensor and transmitter, the PLC modules, the valve, the pumps, and then miscellaneous materials like wires and pipes. Here's a basic wiring diagram of the input side of the system. So basically we have a 24 volt power supply that's being powered by 120 volts AC, and that power supply is powering a 1794 AT module that basically just allows other PLC modules to communicate with the processor over Ethernet, and that's what holds all the logic for the system. Then the PLC module that we're using on the input side is a 1794 IE8. It's basically an analog input card, and that is receiving data from the CM442 transmitter, and that is being powered by 120 volts AC and has a switch on it, and it is receiving data from a sensor that is in the pipes that go to the cooling tower. So here's some pictures of the actual physical equipment that was used in the project, along with schematics. Those schematics were provided in the instruction manuals and data sheets for each respective piece of equipment. And those data sheets were also used to determine how each piece should be wired and set up properly. Here we have the wiring diagram for the output side of the system. So same as with the inputs, we have a 24-volt power supply powering an Ethernet card, which communicates with the PLC processor. In this case, however, we have a 1794 OA16 PLC module, which is a 120-volt AC output. And these are connected to the two chemical pumps and the valve, and they turn on and off the chemical pumps and open and close the valve whenever those outputs are activated or deactivated. So here's some pictures of the pumps, the PLC module, and the chemical barrels, along with the enclosure that the pumps are housed inside of. Now I'll talk about the programming used in this project. So all the actual control for this project was done by Studio 5000 ladder logic. And then there was a Simplicity HMI that was used just kind of to monitor the operation. And then conductivity was graphed over time using a Microsoft SQL database. And so here's a basic flowchart of my program. Pretty simple. From the start of the program, it's going to check if the conductivity transmitter is giving off a 22.5 milliamp signal. If it is, it's going to generate a fault. If it's not, then it's going to check if the conductivity is greater than 1,000 microsiemens per centimeter. And if it is, it's going to open the bleed valve and run the chemical pumps. And it's going to do that for 5 minutes. After 5 minutes, it closes the bleed valve back down and shuts off the pumps. And it's going to wait another 30 minutes and make the same check again. And it'll keep doing that until the conductivity is below 1,000 microsiemens per centimeter. So here's a picture of most of the code that was used to control this project. As I said earlier, it was done with the Studio 5000 logic. And so most of the control was done using comparison operators and then a series of timers to control everything. So here's a picture of the HMI screen that was used, and right there was the addition made to the pre-existing cooling tower screen. And this is just showing what the conductivity is versus the set point. The set point can also be changed by the operator if that's desired, and it shows if the bleed valve is open and the pumps are running. And so here's a graph of the conductivity that's coming out of the cooling tower. So yeah, as discussed earlier, we used a Microsoft SQL server. That's what graphs the historical data for a specific point in Simplicity. So now I'll move on to the operation of the actual project. So I'll show a simulation of the code to show its functionality, and then show a video of the equipment in the plant, so hopefully you can better see the process. So here we can see there's the conductivity sensor measuring water height, and then it sends data to that transmitter, and then over on the far wall is two chemical barrels. That's the chlorine and the fluorine inhibitor. And those are getting pumps there, and then the system. And so this is a simulation of the system with a few modifications just so I could show within a convenient time frame. So right here it goes over 1,000, and that opens the bleed valve, and a little bit after that the pumps start to run. And for the bleed valve, currently I set it to only 10 seconds so that we don't have to wait for 5 minutes for it to close back again. And then, as we'll see in a few seconds, once the conductivity drops below 1,000, right there, the pumps will turn off. So here's a list of all my works cited. This is a list of all the data sheets I referenced. And that concludes this presentation. Special thanks to CH2O, Primary Electric, Alex Arcega, Carrie Roberts, Tony Mancia, and John Kemple for assistance on this project. Thank you.